Now we know what it means to say that f is approximated by its Fourier series. Technically, this means that the Fourier series of f converges in L2 to f as more and more terms of the series are added. And so if we go back to this picture that we were looking at before, where we were looking at the first partial sums of that Fourier series so there's the situation. So the one across the front, this is where we've got one summand, so there's just that one sine function. And then here we have a superposition of two sine functions. So that's the second Fourier polynomial, or the second partial sum in the Fourier series. As we pick up more and more terms of the Fourier series, you see we get a better and better approximation, but there's a couple of things that we saw from before that are still true. So in particular, if we look right along what's going on here at x equals 1/2, we see that it can be the case that the Fourier series can converge to f, but you might have it be the case that the Fourier series at a particular point, like 0 in this case, does not converge to f of 0. So here f of 0 is equal to 1, and the Fourier series for f at 0 is equal to 1/2. But hey, you know what? Sometimes a point here, a point there, it's not going to throw off the value of an integral. And that's why it's possible to converge in L2, but not pointwise sometimes. By the same token, if we look at the max discrepancy between our partial sum and the limiting function, so the limiting function is supposed to take value 1 along this interval right here, and take a look at what we've got, right? So we're off by this much for that first term. That second term is off by this much. For higher terms, we're still always somehow off by about this much. Those peaks happen out here, and the height of those peaks never drops below some line, which is about 9% of the jump distance right here. So this gap right here is about 9% of the height of the jump, in this case being from 0 to 1. And so this is called the Gibbs phenomenon. This overshoot that happens at a discontinuity like this. And so because of this Gibbs phenomenon, the Fourier series for f cannot converge to f uniformly when there's a discontinuity. So the natural choice of what mode of convergence do we use when discussing Fourier series is L2 convergence. And this has a couple of funny implications here and there, like we saw when it didn't converge to the right value at a particular point. So let's see. So there's a theorem that if you start with a function which is in L2, so its square integral converges, then you can prove that the Fourier series of f converges to f in L2. So this is one form of the completeness property that I mentioned before. There's another theorem that's very useful that says that if you stop at any finite point in the Fourier series, then what you have is the best possible approximation to f up to that point, and it's also given by the projection to the corresponding subspace. So this is called the projection or best approximation theorem, depending on what book you're looking at. And it works like this. If W is a subspace of an inner product space V. So if V is an inner product space, then the closest point of W to a general point in the bigger vector space or bigger inner product space V is the projection from V to that subspace W. So in symbols, the distance from V to the projection is the smallest distance from V to points in that subspace. So in the present context, if we take Wn, so if Wn is the span of 1 and cosine x and cosine 2x, and actually here let me intersperse them. So we've got sine x, cosine 2x, sine 2x, and so forth, all the way up to cosine nx and sine nx, where that n is the same n that we chose back here. Then the Fourier polynomial, which is a dumb name for it because it's not a polynomial, but it's called a Fourier polynomial. The Fourier polynomial, which is just the nth partial sum of the Fourier series. Whoops, and that doesn't go up to infinity, that goes up to n, that's sort of the whole point. This is the closest point of Wn to your given function f. So in other words, this Fourier polynomial, this nth partial sum, that is in fact the projection of f to this W sub n. Okay, and since we're in an inner product space, there's a couple other things that we can say, and that is that so let's see, so suppose we've got an orthonormal basis for L2 of some interval I, and we have that f is represented by its generalized Fourier coefficients in terms of this basis as follows. So like this. Then we have a couple of famous identities. So Parseval's identity is that the magnitude squared of f is equal to the sum of the squares of the orthogonal components, which, if you recognize that the squared values of the Fourier coefficients are exactly the magnitudes of Cn un squared, then you realize that this is nothing other than Pythagoras' theorem in infinite dimensions. And we have another very famous theorem, which, when it's written down in terms of integrals, looks exciting and daunting and everything else. But when you see it in this context, it just looks like the obvious observation that if you pull a few of these out, you get something smaller because they're non-negative. So Bessel's inequality states that the magnitude of f is bigger than or equal to any finite truncation of this. And so this is the same thing as the sum up to n of Cn un squared magnitude. And that is exactly the same thing as the projection of f to w sub n. And so Bessel's inequality states the obvious fact that the length of a projection is less than or equal to the length of the original thing. It just states it very nicely and precisely in the context of an inner product space. And so one term that will come up from time to time is we say that an orthonormal set un is complete, or sometimes we say it's total, or sometimes we say it's a basis. All these mean the same thing. If and only if the only thing that is orthogonal to all of these elements is the zero function, or the zero vector. And so this is completely equivalent to the idea that well, let's just leave the indices out of things. That a function is equal to its expansion in terms of this orthonormal set. Always.